Good morning, everyone. I'm happy to be here today and excited to give this talk. I hope it will be informative and enjoyable. This is the outline of my talk. First, I would like to give an introduction and properly define hyperspectral images and what sets them apart from other types of satellite images. And before I go through the methodologies, I will discuss some of the most prominent and used data sets and the quality metrics used to assess them. After that, I will go through two types of methodologies, and finally, I will summarize the current state of the field. So let's take the journey all the way from the start. Remote sensing began in the 1840s as balloonists took pictures of the Earth using newly invented photo cameras. Perhaps the novelist platform at the end of the last century is the famed pigeon fleet that operated as a novelty. And you can see an example of it here in the year 1903. This evolved later after World War II with the inclusion of automated photo camera systems on the captured German V-2 rockets. But the possibility of putting film cameras on spacecraft was not fully realized until 1957 when Sputnik was launched, the world's very first satellite. And then things started to develop rapidly after that. Ever since Landsat was launched in the 70s and with the development of digital image processing, the field of remote sensing kept evolving until finally around 1980, it reached the stage I want to discuss today, which is hyperspectral satellite imagery. This is the hyperspectral image cube. The image has a certain height and width, and then it also has hundreds of bands. It is useful to look at the pixel position value across all bands. For instance, let's say we have a pixel at position 2, 2, and if you look at the value of this pixel across all bands and plot it as such, you can get something known as a spectral signature or spectra. Each material has a unique spectral signature, and this is an important fact to keep in mind for the rest of the presentation. So what is the big deal about hyperspectral images and why do we need them? To answer that, we need to explore the differences between hyperspectral and multispectral images. So the normal images that we know and deal with on a daily basis are RGB images. They just consist of 3 bands. And that is the simplest type of multispectral images. However, they can also consist of a few dozens of bands, but they cannot go over that. On the other hand, hyperspectral images can consist of hundreds of bands. There is a trade-off though. Multispectral images have a limited number of bands, but the height and width of the image it captures is usually big. As for hyperspectral images, it is the complete opposite of that. It has hundreds of bands, but the height and width are tiny. In that sense, we say that multispectral images have high spatial resolution, but low spectral resolution, and vice versa for hyperspectral images. So having high spectral resolution is important and needed for various remote sensing applications, but being limited by the spatial resolution really harms the accuracy at times. So we need to improve the spatial resolution of hyperspectral images in order to be able to utilize their full potential. Normally, when someone researches a topic, they would start by looking into the methodologies available. But I personally think that we should look into the data we have available at our disposal and then decide what to do with this data and how to develop the methodologies and compare between them based on that. There are lots of hyperspectral data available online publicly. So some of them are indoors, other are outdoors. CAVE and Harvard datasets are some of the most widely used. Although CAVE has only 31 bands, scientists still use it to research hyperspectral images, probably because they consider anything higher than 10 bands fitting into the definition of hyperspectral. But other datasets have a much larger number than that. For instance, ICVL has 519 bands. Some datasets are particularly crafted for challenges. For instance, NT-IRE challenge has 2 tracks solely aimed at improving hyperspectral images. Those are some of the data sets that are more relevant to us here since they are taken using satellites. For instance, Indian pines, Pavia, icons, Botswana, and so on. It is important to note that the type of sensor used to capture these images because for certain sensors, some bands would be corrupted or it would be negatively affected. It would negatively affect the analysis due to water absorption. So if we observe the spatial resolution for these images, we have 200 by 300 bands, 140, pixels, not bands, 145 by 145 pixels, and so on. So the size is really small, and this is what we need to enhance. Image enhancement, or proving the visual quality of a digital image, can be subjective. Saying that one method provides a better quality image could vary from person to person. For this reason, it is necessary to establish quantitative empirical measures to compare the effects of image enhancement algorithms on image quality. When we quantify or describe the amount of image enhancement by numbers, we have to have 2 things available to us. The first one is the output from the algorithm, and the second one is the ground truth image, or in other words, the ideal output that we are expecting. So some authors report root mean squared error in their results, but it is not really a very reliable metric. The most reliable ones are the ones listed right beneath it. The term peak signal to noise ratio is an expression for the ratio between the maximum possible value of a signal and the power of distorting noise that affects the quality of its representation. Because many signals have a very wide dynamic range, PSNR is usually expressed in terms of logarithmic decibel scale. So ideally, PSNR should be as high as possible. There is no upper limit for the number you should get. You should aim to get as high as possible. Typically, it would be in the range of maybe late 30s or early 40s decibels. As for the third metric, SSIM, or Structural Similarity Index, it extracts 3 key features from the image: luminance, contrast, and structure. The minimum value it can take is 0, and the maximum value it can take is 1. 0 being that the 2 images are entirely different, and 1 being that the 2 images are exactly the same. Ideally, you will never get a value of 1, but you should aim to get a value that is as close to 1 as possible. Finally, Spectral Angle Mapper is an automated method for directly comparing image spectra to a known spectra or an end member. This method treats both spectra as vectors and calculates the spectral angle between them. The best thing about this method is that it is not sensitive to illumination because it uses vector direction rather than vector length. There are other metrics, of course, but for our purpose today, I'm discussing only these four. And now we can move on to the methodologies. So with the data sets and quality metrics out of the way, we can now move on to this graph in which I'm condensing all the methodologies in one place. We can think of this problem in two different ways. We either fuse multispectral and hyperspectral images together, which will in turn boost the spatial resolution of hyperspectral images. Or we can take single image super resolution approach, which means we boost the spatial resolution without the help of multispectral. To each side, there are advantages and disadvantages, and this is what we are going to get into. Starting with fusion methods, there are two ways to do things here. You can fuse images using traditional methods, otherwise known as optimization methods, or using artificial intelligence and deep learning methods. We will explore optimization methods first. So the first and most straightforward method is pan sharpening. You can find this as a tool available in many commercial software programs. Pan sharpening methods can be broadly categorized into three categories, which are component substitution, multi-resolution analysis, and variational methods. And I will go through the first two only. The simplest method for component substitution is known as Brovie transform. Here in this equation, digital number or DN means pixel value. And we have over here the band of the RGB, and then the band that we wish to enhance. And then finally here, the result gives us the enhanced band. So this needs to be repeated for each hyperspectral band separately. Unfortunately, the injection or the fusion with the multispectral is limited to 3 bands only, and there are constant weights suitable for each satellite. If we don't know what these weights are, we will not be able to implement this method efficiently. Another traditional but popular method is Gram-Schmidt, and the first step here is to obtain a low-resolution version of the panchromatic image, which can be done in many ways, but the most straightforward one is using a low-pass filter. And then the low-resolution pan image is subtracted from the original pan image, which results in a detailed panchromatic band. So this detailed pan band is then injected into the hyperspectral image to boost its quality. And the amount of boosting is determined by something called the gain factor, which is calculated using the covariance and the variance of the hyperspectral intensity component. This method was later enhanced to something called adaptive Gram-Schmidt, and sometimes instead of a simple low-pass filter, people use principal component analysis. So there is a lot to do in here. However, no matter how good the result you get, you will still end up with shortcoming, which I will come to later. But first, I want to discuss the final method, which is intensity hue saturation. Similar to the principle of the methods before, you have to inject the pan band into the hyperspectral image to boost its quality. So in here, this method generates the intensity component by taking the average of all multispectral bands and then subtracts the pan image to obtain the spatial detail matrix. And then these details are injected into the hyperspectral band separately. It is worth mentioning that all of this is done in the lab color domain rather than the domain we are used to, which is RGB. Now, as I said before, component substitution algorithms have shortcomings. Generally, they display remarkable results in terms of spatial resolution. However, they cause spectral distortions, which is their major drawback. And multi-resolution analysis-based algorithms have better resistance to spectral distortions. So MRA-based approaches can be generally conveyed using the following equation, where this component denotes the kth band of the estimated upsample hyperspectral image, and this component denotes element-wise multiplication. This is the pan band, and this is the low-pass version of the pan band. And each multi-resolution analysis algorithm differs in the way they derive the PL and the GK, which is the gain factor. So one example we have is the smoothing filter-based intensity modulation. It's a pan-sharpening technique that is obtained from a linear time-invariant low-pass filter, such as the averaging filter. And for the injection factor, a high-pass modulation can be utilized. And as usual, the result of this is injected into each hyperspectral band separately. And like every other method we have discussed so far, there are advantages and disadvantages. For instance, MRA have temporal coherence, spectral consistency, robustness to aliasing. However, the implementation is much more complicated due to the design of spatial filter, and the computational complexity places a burden much larger compared to component substitution methods. So let's move on from pan sharpening and start discussing a much more intriguing concept and a very important one when discussing hyperspectral images, and that is spectral unmixing. This is the procedure by which the measured spectrum of a mixed pixel is decomposed into a collection of constituent spectra or end members, and a set of corresponding fractions or abundances that indicate the proportion of each end member present in the pixel. It is expressed as the following equation, where this is the spectral vector expressed by a linear combination of several end member vector. And this is the number of end member vectors inside the pixel. This setup can be fully exploited using a concept called matrix factorization, and it works as follows. The relationship between low and high spatial resolution of hyperspectral images can be expressed as follows, where S is the spatial transform matrix, and this component represents the residual error. S is determined by image registration and estimation of point spread function. Similarly, the relationship between low and high spectral resolution and multispectral can be described as follows, where R is the spectral information matrix, and this over here is the residual error. R can be derived from radiometric calibration to obtain spectral response function. So from these two equations, hyperspectral and multispectral can be expressed as follows, and NHS and NMS are the residual error matrices. Now, matrix factorization in spectral unmixing is commonly performed to minimize the squared Frobenius norm of the residual error matrices, which is expressed as such. Assuming that the hyperspectral and multispectral images capture the exact same scene, their end members should be exactly the same, and the abundance map should be exactly the same as well. And then the abundance matrix from the multispectral can be extracted from it and then used to enhance the spatial resolution of the hyperspectral image, which can be finally estimated, as we can see here. So the abundance matrix expressed as H is taken from the multi-spectral. There are many ways and many variations in which this can be done. For instance, we have KSVD, Bayesian sparse representation, and there are also dictionary learning methods where two dictionaries are learned from the hyperspectral and multispectral, and then dictionary pair learning method is used to establish correspondence between them. Again, the disadvantages and disadvantages here are a bit more complex. For instance, one shortcoming of the matrix factorization approaches is that they require good initial point of the two decomposed reflectance signatures to provide satisfactory results. If we don't have good initial points, the algorithm will not work. Most work generally assumes that the number of pure materials in the observed scene is smaller than the number of spectral bands, which is not always the case. And but here, if we did a quick visual comparison between the component substitution and matrix factorization to their ground truth, we can see that matrix factorization is visually much closer to the ground truth than component substitution. And this takes us away from traditional optimization methods to the convolutional neural networks. Just a little introduction at first. Convolutional neural networks are a subset of neural networks, which are in turn a subset of artificial intelligence. So artificial intelligence is the big umbrella here. And when a convolutional neural network has so many layers inside it, like this one here, we call it a deep convolutional neural network, or DCNN for short. DCNNs have already proven superiority in so many image processing tasks, including classification, object detection, and segmentation. So it is natural to discuss them in the context of image fusion. A DCNN can typically improve either spectral resolution or spatial resolution. However, to each one of these, there are certain shortcomings. So, for instance, enhancing the spatial resolution by itself imposes limitations such as you can enlarge the image by a factor no bigger than 8. And on the other hand, enhancing the spectral resolution ignores the correlation between the narrowbands. Therefore, Fusion DCNN attempts to overcome these limitations by utilizing both spatial and spectral enhancement. And that is why the network we are seeing over here is called Spatial Spectral Fusion, or SSFNet for short. So SSFCNN architecture takes the concatenated cubic data of the high-resolution RGB image and upsampled low-resolution hyperspectral image as inputs simultaneously to learn spectral attribute from the hyperspectral image, and at the same time learn the spatial context from the multispectral or RGB image in order to achieve more robust high-resolution image estimation. There are also short connections here between the input layer and the learned feature map in order to concatenate data directly from here to there, which also boosts the learning process. This is an overall comparison between the optimization methods discussed and SSFNet. So we have 3 different quality metrics: RMSE, PSNR, and SAM. And in each and every quality metric, SSFNet, which is a DCNN, prevails in all of them. So we can see that the PSNR is about 42, RMSE is 2.1, and SAM is 3.98. Ideally, these two should be as close to 0 as possible, but these are acceptable values. So even when you do a visual comparison over here, you can see that the SSFNet is closer to the grounded truth image, as opposed to the other algorithms, including the traditional ones and also the spatial and spectral ones. And now we can leave fusion approaches and move on to the other approach, which is single image super resolution. I will repeat this again. The idea is that we do not rely on auxiliary information from multispectral images. We only rely on the single low resolution hyperspectral image that we are trying to improve. And that is why SISR is known in the literature as a notoriously ill-posed problem, because we are trying to estimate high-frequency components which are responsible for image details, and we do not have any guidance for it. We are trying to estimate something that we are completely blind about. Traditionally, you can enhance the spatial resolution of an image, any image at all, be it hyperspectral or not, through interpolation methods. Here, I'm only discussing bicubic interpolation because it is the most widely used one and it has a decent performance. So this method maps image values from one space to another. In this case, from a 4x4 space to an 8x8 space. And then it estimates the missing empty values in between. The estimation does not come from one side, like it's not only horizontal or only vertical. Estimation has to be both horizontal and from both non-horizontal and vertical values. The problem with this method is that no matter how decent the performance is, you will always end up with blurriness and loss of image details and high frequency components. And this is another problem that deep convolutional neural networks attempt to eliminate. The simplest DCNN that performs super resolution is called super resolution CNN, or SRCNN for short. It consists of 3 layers only, and all of them are convolution layers. So we have here a 9x9 convolution layer, which results in 64 channel features. 5x5 convolution layer results in 32 channel features. And then finally, another 5x5 convolution layer, which gives us our intended output. So this network is divided into 3 parts. The first part is responsible for patch extraction. Second part is responsible for nonlinearity mapping from the input to the feature maps. And then the final part is responsible to reconstruct the high resolution hyperspectral image from the feature maps it managed to learn. However, this network acts in 2 dimensions, and hyperspectral images, as we have seen, consist of a big cube of bands, as I mentioned at the beginning of the talk. So having a network with layers that are all 2-dimensional can cause spectral distortions in the enhanced output. And that is why some researchers argue that 3D convolutional neural networks are the best for enhancing hyperspectral images. Here, for instance, we have one example of that, which is frequency-separated 3D CNN. The idea is very simple. We have 2 parts of the network. The first part on the left extracts the features, and the second part on the right is the prediction, or in other words, the reconstruction part. All the convolution layers perform convolution in 3D, unlike the network we have previously seen. And the image here is processed in the wavelet domain. The wavelet domain splits the image into 4 components. The first component is the low resolution one, or approximation. Second one is horizontal details, then vertical details, and finally diagonal details. Each one of these components is processed through the network separately. And at the end, when we obtain the output of each one, we concatenate them back together and perform inverse wavelet transform to obtain the final output. We can see again that this network here benefits from connections to take information from the input and add them to the feature maps directly, which boosts the learning process. Here, we have a network called MCNITT. This network mixes between 2D and 3D. The reason is that some authors argue that the network does not have to be purely 2D or purely 3D. In fact, they can benefit from combining both. The 3D part of the network prevents spectral distortions, while the 2D part of the network focuses on the spatial enhancement. And this is one network that does exactly that. This is the overall architecture of MCNITT. The whole network mainly consists of 3 parts. First, the low-resolution hyperspectral image is fed into the initial feature extraction subnetwork. Then these shallow features go through several mixed convolution models, 2D and 3D, in addition to skip connections to obtain depth features of the hyperspectral image in deep feature extraction subnetwork, which is right here in the middle. And finally, these feature maps are upsampled according to the scale factor in the image reconstruction subnetwork. One disadvantage of this is that it suffers from a high memory footprint, unfortunately. It consumes a lot of memory, and it is also very computationally extensive. And that is because it is a complicated network and it's processing each band by itself. So if the hyperspectral image is if it consists of, I don't know, 200 plus bands, that means this network has to repeat the work 200 plus times. And that is why SFCSR network exists. It is inspired by the high similarity among adjacent bands. It is yet another mixed 2D and 3D convolutional neural network. So it's a dual channel, and it exploits information from both single band and adjacent bands, which is different from all the previous works we have seen. Under the connection of depth split, it can effectively share spatial information so as to improve the learning ability of 2D spatial domain. And besides, this method introduces the features extracted from previous bands, which contributes to the complementarity of information and simplifies the network structure. Through feature context fusion, it significantly enhances the performance of the algorithm. We can see here a quick comparison in terms of PSNR, SSIM, and SAM between bicubic, SRCNN, frequency-separated 3D CNN, MCNITT, and finally SFCSR. And evidently, SFCSR has the highest performance in terms of PSNR, SSIM, and also in terms of SAM. And not so surprisingly, bicubic shows the lowest performance. We can benefit from a visual comparison as well. This is an absolute error map where blue color denotes 0 error and the red color denotes 100% of error. So if we take a quick look here, we can see that bicubic has the highest number of errors here, followed by SRCNN, and then 3D CNN, and then MCNITT, and finally SFCSR shows the best error map among all of them. So to summarize this talk, we have discussed fusion methods and single image super resolution methods. And broadly, we can say that the advantages of single image super resolution are the disadvantages of fusion methods and vice versa. For instance, single image super resolution methods have no need for auxiliary information. And this is an advantage because we do not have to worry about image registration between multispectral and hyperspectral. On the other hand, fusion methods, even though they require prerequisite knowledge, they have high scaling factor and spectral consistency, much better compared to single image super resolution, which cannot go past the scaling factor of 8. So each one of these two fields have a certain gap that still needs to be improved. However, if we look at the number of papers published in the classical methods or traditional methods compared to convolutional neural network methods, we can see that researchers are slowly starting to abandon traditional methods and shift entirely to convolutional neural networks. And this has been evident in the most recent 3 years. So it seems that there is a unanimous agreement that deep convolutional neural network methods prevail over the traditional ones. So to sum up, as I said before, the future direction of this field seemed to be fully headed towards deep convolutional neural networks. There is an abundant amount of data out there that are just waiting for someone to research them and enhance the algorithms that we already have. But when developing one, there are things we need to keep in mind, such as the scaling factor, the spectral distortion, and the computational cost. So whether fusion methods are better than SISR methods or vice versa, there is no right or wrong answer. Each one of them have different advantages and disadvantages, and the method of choice depends on the type of data and information that you have. And this concludes my talk. I hope that this has been fun, and thank you so much for your attention.